Dark energy and dark matter. A detailed note: the universe is a vast and mysterious expanse, and much of its composition remains elusive. Scientists have discovered that the cosmos consists not only of the familiar matter and energy we encounter daily but also of two enigmatic components: dark energy and dark matter. These account for about 95% of the universe, profoundly influencing its structure, evolution, and ultimate fate. Dark matter. What is dark matter? Dark matter refers to an unseen form of matter that neither emits, absorbs, nor interacts significantly with electromagnetic radiation, making it invisible to telescopes. However, its existence is inferred through its gravitational influence on visible matter, radiation, and the large-scale structure of the universe. Evidence for dark matter. 1. Galaxy rotation curves. In spiral galaxies, the rotational speed of stars does not decrease with distance from the galactic center as predicted by Newtonian dynamics. Instead, it remains roughly constant, suggesting the presence of a massive, invisible halo of dark matter surrounding galaxies. 2. Gravitational lensing. When light from a distant galaxy or quasar passes near a massive object, such as a galaxy cluster, the light is bent. The amount of bending indicates the presence of far more mass than visible matter alone can account for, implying dark matter. 3. Bullet cluster observations. In this famous collision of galaxy clusters, the visible matter, hot gas, and gravitational effects, measured through lensing, or offset. This provides direct evidence of dark matter being separate from baryonic matter. 4. Cosmic microwave background, CMB. The CMB shows fluctuations that reflect the density of matter in the early universe. Analysis of these fluctuations supports the existence of non-baryonic dark matter. 5. Large-scale structure formation. Simulations of galaxy formation require dark matter to explain the observed structure of the universe, as visible matter alone could not clump fast enough under gravity. Theoretical models of dark matter. 1. Weakly interacting massive particles, WIMPs, hypothetical particles that interact via the weak nuclear force and gravity. Predicted by supersymmetry theories and could be detected through direct or indirect methods. 2. Axions, extremely light particles proposed to solve the strong CP problem in quantum chromodynamics, QCD. Could form a component of cold dark matter. 3. Sterile neutrinos, a type of neutrino that does not interact via the weak nuclear force, making it sterile. Potentially detectable through its decay into lighter neutrinos and photons. 4. Modified gravity theories. Alternative explanations such as modified Newtonian dynamics, MOND, attempt to describe the observed phenomena without invoking dark matter, though they lack widespread acceptance due to insufficient evidence. Challenges in detecting dark matter. 1. Direct detection. Experiments like Lux-Zeppelin and Xenon-1T aim to observe dark matter particles interacting with ordinary matter. 2. Indirect detection. Looks for products of dark matter annihilation or decay, such as gamma rays or neutrinos, using telescopes like Fermi. 3. Collider experiments. Searches at facilities like the Large Hadron Collider, LHC, for particles predicted by dark matter models. Dark energy. What is dark energy? Dark energy is an unknown form of energy that constitutes about 68% of the universe and is responsible for its accelerated expansion. Unlike dark matter, which clusters and forms structures, dark energy is uniformly distributed throughout space. Evidence for dark energy. 1. Type Ia supernovae observations. Distant supernovae appear dimmer than expected, suggesting that the universe's expansion is accelerating. This implies a repulsive force attributed to dark energy. 2. Cosmic microwave background, CMB. Measurements of the CMB reveal the universe's flat geometry. This flatness requires a significant contribution from dark energy to balance the energy density. 3. Baryon acoustic oscillations, BAOs. The distribution of galaxies shows patterns consistent with the effects of dark energy altering the rate of cosmic expansion. 4. Large-scale structure evolution. The growth of galaxy clusters slows down due to dark energy's repulsive effects counteracting gravitational attraction. Theoretical models of dark energy. 1. Cosmological constant, lambda, first proposed by Einstein as a modification of his general theory of relativity. It represents a constant energy density inherent to the fabric of space. Fits well with current observations but raises questions like the fine-tuning problem. 2. Quintessence, a dynamic field whose energy density can evolve over time. Offers flexibility compared to a cosmological constant but introduces additional parameters. 3. Modified gravity theories. Theories such as gravity or extra-dimensional models propose modifications to Einstein's equations that mimic the effects of dark energy. 4. Vacuum energy. Related to quantum field theory, where empty space is thought to have energy. The predicted value, however, vastly exceeds observed values, leading to the cosmological constant problem. Challenges in understanding dark energy. 1. Its nature remains deeply mysterious, as it defies conventional physics. 2. Observational constraints are limited, and distinguishing between different models requires more precise data. 3. Future missions like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope aim to refine our understanding. Implications of dark energy and dark matter. 1. Cosmic fate. The balance between dark energy and dark matter determines the universe's ultimate fate. Big freeze. The universe expands forever, cooling as galaxies drift apart. Big rip. Accelerated expansion tears apart all structures, including atoms. Big crunch. If dark energy weakens, gravity might eventually reverse the expansion. 2. Structure formation. Dark matter governs the formation of galaxies and large-scale structures, while dark energy shapes the large-scale dynamics of the universe. 3. Unification of physics. Understanding dark energy and dark matter could reveal new physics beyond the standard model, linking quantum mechanics, general relativity, and cosmology. Conclusion: dark energy and dark matter are cornerstones of modern cosmology, accounting for about 95% of the universe's total energy density. While dark matter acts as an invisible framework for the cosmos, dark energy drives its accelerated expansion. Despite decades of research, their nature remains elusive, posing profound challenges and opportunities for science. Future advancements in observational technology, particle physics, and theoretical modeling may unlock these cosmic mysteries, reshaping our understanding of the universe's origins, evolution. Supersonic cracks. A detailed explanation. Supersonic cracks are a fascinating phenomenon in the field of fracture mechanics, where a crack propagates through a material at speeds greater than the speed of sound in that material. This behavior, while rare and specific to certain conditions, has profound implications in materials science, earthquake dynamics, and structural failure analysis. Background and fundamentals. What is a crack? A crack is a discontinuity or fracture in a material. It forms under stress when the material's cohesive forces are overcome. 1. Subsonic cracks. In most cases, cracks propagate at speeds slower than the material's sound speed, Cs, limited by energy dissipation and stress wave interactions. 2. Supersonic cracks. Under certain conditions, the crack tip accelerates beyond the material's shear wave velocity, Cs, or compressional wave velocity, Cp. Wave speeds in materials. In solids, two key wave speeds dictate the propagation of stress waves. Shear wave velocity, Cs equals sqrt mu, ρ, mu, shear modulus. Rho, material density. Compressional wave velocity, Cp equals sqrt lambda plus 2 mu, ρ, lambda. Lamè's first parameter. Cp, Cs. Supersonic cracks occur when the crack tip velocity, Vc, exceeds Cs or, in rare cases, Cp. Conditions for supersonic cracks. Supersonic cracks are not typical and require 1. Material properties. Brittle materials with high elastic moduli and low plasticity are more likely to exhibit supersonic cracks. Examples: glass, ceramics, and some polymers. 2. Loading conditions: high strain rates and dynamic loads. Examples: explosions, impacts, or rapid stress release. 3. Geometrical factors: pre-existing flaws or sharp stress concentrators. Specific crack orientations relative to stress fields. Physics of supersonic crack propagation. Energy considerations: crack propagation requires energy to 1. Overcome material cohesion, fracture energy, g. 2. Create new surfaces at the crack tip. In supersonic cracks, 1. The energy release rate, g, exceeds the fracture toughness, gc. 2. The dynamic stresses at the crack tip become localized due to shock wave formation. Stress wave interactions: 1. At subsonic speeds, Vc. 2. At supersonic speeds, Vc, Cs, stress waves lag behind the crack tip, forming a Mach cone similar to a sonic boom. The stress intensity at the crack tip increases sharply, which can destabilize the material. Dynamic fracture mechanics: the equation governing crack tip velocity, Vc, is influenced by 1. The material's elastic constants. 2. The stress intensity factor, K. 3. The energy release rate, G. For supersonic cracks, modifications to classical theories, like Griffith's theory, are needed to account for nonlinear effects and wave mechanics. Types of supersonic cracks: A. Shear supersonic cracks. 1. Crack propagates with velocity exceeding the shear wave speed, Cs. 2. Observed in dynamic shear failure or earthquake faults. 3. Example: ruptures along faults during earthquakes. B. Intersonic cracks. 1. Velocity between Cs and Cp. 2. Common in Mode 2, in plane shear, fractures. 3. Example: polymer or composite materials under dynamic shear loading. C. Transonic cracks. 1. Velocity near or slightly above Cp. 2. Extremely rare due to the instability of stress fields at these speeds. Experimental observations: supersonic cracks are difficult to observe directly due to their transient nature. However, advanced experimental techniques have provided insights. 1. High-speed cameras capture crack dynamics in brittle materials under high-speed loading. Example: glass shattering under explosion. 2. Stress wave analysis detect stress waves using piezoelectric sensors or strain gauges. Measure stress intensity and crack velocities. 3. Numerical simulations finite element models simulate stress distribution and wave propagation. Examples: simulations of earthquake fault dynamics. Applications and implications. A. Earthquake dynamics. 1. Supersonic cracks, called supershear ruptures, occur in earthquake faults, producing high-velocity seismic waves. 2. Consequences: amplified ground motion near faults. Enhanced destruction in populated areas. Material failure analysis. 1. Understanding supersonic cracks helps design materials resistant to dynamic failure. 2. Applications: aerospace, impact resistance in aircraft materials. Construction, seismic-resistant structures. Shock physics. 1. Supersonic cracks are relevant in studying explosive fragmentation and shock wave interactions. 2. Example: military and defense applications. Challenges and open questions. Despite advancements, challenges remain in understanding supersonic cracks. 1. Theoretical limitations extending fracture mechanics to account for nonlinear stress fields in wave interactions. 2. Material behavior determining why some materials resist supersonic cracks. 3. Real-world scenarios linking laboratory-scale observations to large-scale phenomena like earthquakes. Conclusion: supersonic cracks are a complex and fascinating phenomenon where material failure interacts with wave mechanics. They bridge the gap between fracture mechanics, dynamic systems, and material science, with far-reaching implications in fields like geophysics and structural engineering. Further research is crucial to fully understand their behavior and mitigate their destructive effects.